మ్యూట్ పెట్టుకోనా?
ఇష్టం.
ఇందాక మ్యూట్ పెట్టలే, శబ్దం వెళ్ళిపోతుంది. యూట్యూబ్లో అప్లోడ్ చేస్తారు వీటి మళ్ళీ. తీసేయండి. Hello students, last class in the last class I have discussed about groups, subgroups, normal subgroups and their properties, and also we have discussed about homomorphisms, isomorphisms, endomorphisms, epimorphisms and all. Today I am going to give an introduction about ring, which all of you know in your degree classes. What is a ring? An algebraic structure R plus dot is called a ring if R plus is an abelian group, R dot is a semi-group, and R satisfies distributive laws. That is, A into B plus C is equal to A into B plus A into C. And at the same time, B plus C into A. B plus C into A is B into A plus C into A. So we say that R is a commutative. R is a ring is said to be a commutative ring if we A into B equal to B into A. And we say that a ring R has identity element 1 if 1 into A equal to A into 1 is A for every A belongs to R. So if each non-zero element possesses multiplicative inverse, then we say that B into A is equal to A into B equal to 1. We say that B is the inverse of A. Now, a commutative ring with the unity is called an integral domain if it has no zero divisors, or if a ring is without zero divisors. What do you mean by that? We say that ring is without zero divisors if A into B equal to 0 implies either A equal to 0 or B equal to 0, then we say that ring is without zero divisors. For example, if you take 3 into 2 under modulo 6, 3 into G is nothing but 3 2s are 6. 6 when divided by 6 leaves the remainder 0. But here 3 not equal to 0, 2 not equal to 0. So we say that ring is having zero divisors. Without zero divisors means the product of two numbers is 0 only when one of them is 0. Zero divisors means we can find matrices also. You can find two matrices A and B such that AB equal to 0, but A not equal to 0, B not equal to 0. So such a kind of ring is known as integral domain. So here we say that field. What do you mean by field? A commutative ring with the unity in which each non-zero element possesses multiplicative inverse is called a field. A field is a commutative ring with unity in which each non-zero element possesses multiplicative inverse. So clearly we can say that every field is an integral domain. Integral domain need not be a field, but every finite integral domain is a field. Every finite integral domain is a field. All of you know this. In this commutative algebra, we are going to study extension of this. But before entering into commutative algebra, let us define one important concept of the ring called ideal of a ring. What do you mean by ideal of a ring? A non-empty subset S of R is said to be an ideal if A comma, if first one S is a subring with respect to addition. That means A comma B belongs to S implies A minus B belongs to S. And the second one, R is element of ring, R belongs to R, and A belongs to S, implies RA, comma, AR belongs to S. That is, we say that if ring element is on the left side, then we called it as left ideal, and AR means ring element is on right side, it is right ideal. Suppose if you take R is a commutative ring, there is no distinction between the ideals. Every left ideal is the same as right ideal. So in a commutative ring, we have every left ideal is a right ideal. An ideal is said to be principal ideal generated by A. What do you mean by principal ideal? Is we say that S is principal ideal. That means if S is generated by A, that is S contains all the elements of multiples of A. Then we say that R is a principal ideal. Okay, every ring itself is an ideal. Zero element is always an ideal. These two are called improper ideals. Other than any two, these are called improper ideals. That means we can say easily that a field has no proper ideals. Why? Because only the ideals of field are 0 and F itself. Let us not go in detail about this because we have studied in algebra already in first year. So just I am giving one outline of these ideals, principal ideal. What do you mean by prime ideal? What do you mean by a prime ideal? An ideal S of ring R is said to be a prime ideal if AB belongs to S, implies either A belongs to S or B belongs to S. A belongs to S or B belongs to S. And we say that maximal ideal, an ideal S is said to be a maximal ideal if S is not contained in any other ideal. If S is not contained in any other ideal. That means if you have S is a subset of U is a subset of R, implies either U equal to S or U equal to R. That means it is S itself is the maximal ideal contained in the ring R. So here S is not contained in any other ideal. All the ideals are sub-ideals of S. Then only we say that S is a maximal ideal. And we know that quotient ring. What do you mean by quotient ring? Here also you can define ideals. Not ideals, what do you call it? Cosets. R by S is the set of all S plus A such that A belongs to R is a quotient ring with respect to addition and multiplication of ideals. You have S plus A plus S plus B equal to S plus A plus B. S plus A into S plus B is equal to S plus AB. With respect to these two operations, you have R by S is a ring called a quotient ring. R by S is a quotient ring. Now you have if R is a commutative, then R by S is a commutative ring. And we know that R by S is an integral domain. R by S is an integral domain if S is a prime ideal. And R by S is a field if S is a maximal ideal. Okay, with this knowledge about rings and fields, we will enter into commutative algebra. See, first of all, let us discuss about primary decomposition and associated primes. We know almost modules and all. Just these are the, which one? Ring theory background. Almost I explained all this. Next. Jacobson radicals, local rings, and other miscellaneous concepts which we want to know here. See here, let Jr be the Jacobson radical of the ring R. That is the intersection. What do you mean by Jacobson ring J of R? J of R is the intersection of all maximal ideals of R. It is the intersection of all maximal ideals of R. Jr is J of R is intersection of M, where M is a maximal ideal. Now, this theorem is important for 5 marks. Let J of R be the Jacobson radical of the ring R. That is the intersection of all maximal ideals of R. Then A belongs to JR if and only if 1 plus AX is a unit. What do you mean by unit? Unit means you have A into, we say that B is an unit if A into B is 1. Or we say that B is the inverse of A, or A is a unit, which has multiplicative inverse is a unit. So we say that then A belongs to JR if and only if 1 plus AX is a unit for every R. Assume that A belongs to JR. Assume that A belongs to JR. That is Jacobson radical of ring R. And if what will happen if 1 plus AX is not a unit, then it generates a proper ideal. Isn't it or not? So if it is not an ideal means it generates a proper ideal. Hence, 1 plus AX belongs to some maximal ideal M. What do you mean by maximal ideal? You have A belongs to M, X belongs to R. X belongs to R implies AX belongs to M. AX belongs to M and therefore you have 1 belongs to M, which is a contradiction. Why? Because you have 1 plus AX belongs to M. Okay. Now X belongs to R, A belongs to M implies AX belongs to M by definition of ideal. Ideal means one ideal element A belongs to M, X belongs to R implies AX belongs to M. That means what do you mean by that? 1 plus AX minus AX belongs to M because M is a subring of the ring. So you have 1 belongs to M. 1 belongs to M means what will happen? M will become R. So this is a contradiction. Therefore, that means you cannot have M as a maximal ideal. Therefore, that means it has no proper ideals. If 1 plus AX is not a unit, it generates a proper ideal. It generates a proper ideal means it cannot be a maximal ideal. J of R cannot be a maximal ideal. Similarly, conversely, suppose if what will happen if A does not belongs to M? If A does not belongs to M, then you know that M plus RA is R. That is for some B belongs to M, B belongs to M and Y belongs to R, you have B plus AY is 1. Or if you take X is minus Y, then you have 1 plus AX which is equal to B belongs to M. What do you mean by this? That means 1 plus AX cannot be a unit. Therefore, you have 1 plus AX is a unit if and only if A belongs to JR. Then, see, let capital M be a maximal ideal. Next lemma, or you can take it as a theorem also. Let capital M be a maximal ideal of the ring R. Then R is a local ring. What do you mean by local ring? A ring with a unique maximal ideal. It is a ring, it's a unique maximum ideal, maximal ideal. That is, if and only if 1 plus M is a unit. 1 plus M is a unit. Suppose R is a local ring. If R is a local ring and A belongs to M, if 1 plus A is not a unit, what will happen? Then 1 plus A belongs to M, which is ideal of non-units. So, but 1 belongs to M is a contradiction. Conversely, assume that every element of 1 plus M is a unit. We prove that M is JR. Okay, already JR is subset of M and D. So, M is a subset of JR. If you prove, we are done. If A belongs to M, then AX belongs to M for every X belongs to R. So you have 1 plus AX is a unit. So by above theorem, and whenever 1 plus AX is a unit, you have A belongs to JR. Therefore, if N is any other maximal ideal, then M is equal to JR, which is a subset of M intersection N. So you have M is a subset of N. Since both ideals are maximal ideals, here M is a maximal, N is a maximal ideal, then both must be equal. So therefore, R is a local ring. That means R cannot have two maximal ideals. Then we say that R is a local ring. Students, are you following? Hello? Next one. See, let S be any subset of R. Let just go through this theorem proof. Now, let S be any subset of R and I be the ideal generated by S. Then I is equal to R if and only if for every maximal ideal M, there is an element X belongs to S by M. So we have I is a subset of R if and only if I equivalently S is contained in some maximal ideal M. That means maximal ideal means there is no ideal between M and R. So you have, in other words, you have I is a subset of R if and only if there exists M such that X belongs to S. Implies we have X belongs to M. So by contrapositive, we have I equal to R. If and only for every M belongs to M, for every M, there exists X belongs to S such that X does not belong to M. All of you know what, I hope you know, contrapositive. P implies Q. If and only if negation of Q implies negation of P. Now let I comma J be ideals of ring R. let I comma I and j be ideals of the ring R, then I plus j equal to R if and only if root I plus root j equal to R. Okay, because definitely one part I plus j equal to R implies definitely root I plus root j belongs to R, because any ideal is contained in its radical. So assume that I is equal to a plus b with am belongs to I and bn belongs to j. What is 1, Andy? What do you mean by 1 is a plus b whole power m plus n, which is equal to m plus n I ai power bj, because by binomial expansion this one. So if I plus j is m plus n, then either I greater than or equal to m or j greater than or equal to n. So we expand, this means every term in the sum belongs to either I or to j, because every sum, because I is an ideal. Ideal means it satisfies all the closure property. So it satisfies closure property. So you have 1 belongs to I plus j. These are the prerequisites. And the next one is, let capital M be finitely generated R module, and I is an ideal of R such that I into M is M. Then there exists A belongs to I such that 1 plus A into M is 0. Just to go through this proof. Just students, once you are familiar with all basic concepts of ring, fields, ideals, homomorphisms and isomorphisms, we will do important theorems of commutative algebra. Hello, today one student joined named Kavita, isn't it? Hello? Hello? Hello, are you there? Hello? Then next theorem is, see definitions, you see, if P is a prime ideal of R, then we have say that multiplicative S equal to R minus P is a multiplicative set. In this case, we write RP for S inverse R. We call it as the localization of R at P. So we are going to show that RP is a local ring, that is a ring with unique maximal ideal, ring with unique maximal ideal. So here we are going to give some equivalent definitions of local ring. You see, for a ring R, the following conditions are equivalent. R is a local ring. There is a proper ideal of I of R that contains all non-units of R. The set of all non-units of R is an ideal. Already this you must be studied in algebra. So just to see, what do you mean by R is a local ring? R is a local ring means we have to prove that there is there is a proper ideal I of R that contains all non-units of R. So if A and B are non-units, so A plus B is a non-unit, RA is also non-unit. Otherwise, what will happen? I contains a unit element. If I1 belongs to I, that means we from rings, we know that always if U is an ideal, U is a subset of R. Then if 1 belongs to U, then there is no difference between U and R. So if unity belongs, that means if A and B are non-units means A plus B is a non-unit, RA is also non-unit. Okay, if not, what will happen? I equal to R. So contradicting the hypothesis. Similarly, 3 implies 1. If I is the ideal of non-units, definitely maximal ideal. While doing maximal ideals, we have seen that become R. So if H is any proper ideal, H cannot contain a unit. So H is the subset of I. So you have, therefore, I is the unique maximal ideal. So I think everybody has understood the concept of local ring. RP is a local ring. What is RP? S inverse R. Let Q be a maximal ideal of RP. If Q is a prime ideal, so you have Q is S inverse I. For some prime ideal I of R that is disjoint from S equal to R minus P. In other words, I is a subset of P. Consequently, you have Q equal to S inverse I, which is a subset of S inverse P. If S inverse P is RP, which is nothing but S inverse R. So we have proved that S inverse P is a proper ideal containing every maximal ideal. S inverse P is a proper ideal containing every maximal ideal. So it must be the unique maximal ideal. So this is the localization of modules. If M is R module and S is a multiplicative subset of R, we can construct to form localization of M by S. We define like this: X by S plus Y by T is just LCM తీసుకుని చేయండి. You have A by S belongs to S inverse R, X by T belongs to S inverse M. So we define AX by ST is equal to AX by ST. In this way, S then S inverse of M plus N, this one. So these are all what all I am teaching is, these are all prerequisites for commutative algebra. To learn commutative algebra, just 2 weeks, I am focusing only on the definitions. So if you want to enter into the syllabus, you have primary definitions. Let n be a submodule. If m is a n is a submodule of the R module m and a belongs to R, then lambda a from m by n to m by n is a multiplication by a. We say that n is a primary submodule of m. Listen carefully. We say that n is a primary submodule of m. If n is proper and for every a, lambda a is either injective or nilpotent. Injective means, we know one, injectivity means for all x belongs to m, there exists ax belongs to n, implies x belongs to n. Nilpotence means that for some positive integer n, a power n m is a subset of n. That is, a power n belongs to the annihilator of m by n. Annihilator of m by n, denoted by a annihilator of m by n. Equivalently, a belongs to the radical of the annihilator of m by n. Radical of annihilator of m by n is denoted by R m n, radical of annihilator of m by n. But at the same time, what is the point to be observed? Lambda suffix a, lambda a cannot be both injective and nilpotent. If it is injective, then it cannot be nilpotent. If it is nilpotent, then it cannot be injective. So nilpotence gives a power n m is equal to a into a power n minus 1 m, which is the subset of n. And injectivity gives a power n minus 1 m is a subset of n. Inducively, you have m is a subset of n, and n is an ideal, m is maximal, means m equal to n. So contradict the assumption that n is proper. Therefore, if n is a primary submodule of m, then Rmn, R suffix mn, is the set of all a belongs to R such that lambda a is not injective. So Rmn is the radical of an ideal. It is an ideal of R. In fact, it is a prime ideal. If I is an ideal of R, then R suffix R I is root I, because annihilator of R by I is I. Note that A belongs to annihilator R by I, if and only if AR is the subset of I, if and only if A equal to A1 belongs to I. So specializing to M equal to R and replacing A by Y, we define primary ideal. What is the primary ideal in a ring R? as a proper ideal Q such that if xy belongs to Q, then either x belongs to Q or y power n belongs to Q for some n greater than or equal to 1. Okay, equivalently, we have r by q not equal to 0 and every zero divisor in r by q is nilpotent. If root I is the maximal ideal, then I is M primary. What do you mean by M primary? Suppose AB belongs to I and B does not belongs to root I equal to M, then maximality of M, it follows that M plus RB is R. So for some M belongs to M and small r belongs to capital R, we have M plus RB is 1. Now M belongs to capital M, which is equal to root I. Hence M power K belongs to I for some K greater than or equal to 1. All this we have to remember these points. What do you mean by primary decomposition? A primary decomposition of submodule N of M is given by N is the intersection of N1, N2, etc. Nr, where Ni and Pi are primary submodules. The decomposition is reduced. The decomposition is reduced if Pi are distinct and N cannot be expressed as the intersection of proper subcollection of Ni. See, whenever you learn commutative algebra, mainly focus on the definitions only. If you are perfect with definitions, it is easy for you to learn the theorem. A primary decomposition of the submodule N of M is given by N equal to sigma I is equal to 1 to R, sigma N equal to intersection I is equal to 1 to R Ni, where the Ni are Pi primary submodules. The decomposition is reduced if the Pi are distinct and N cannot be expressed as the intersection of proper subcollection of Ni. Next, see this one lemma. If N1, N2, etc., Nk are P primary, then Ni is also pre-primary. So we assume, we prove by mathematical induction, we can easily prove this theorem. See, next definition. The proper submodule N of M is irreducible. Irreducible means it cannot be reducible. That means it cannot be expressed as the intersection of any two sets. So you have, if N is an irreducible submodule of Noetherian module, then N is a primary module. So next week, we are going to learn about primary decomposition, Noetherian and Artinian rings.